Chapter 5, the laws of motion. In this chapter, we're going to study the beginning of dynamics. We have so far focused on what's called kinematics, which is a branch of mechanics. In kinematics, we're focused on the subject of how to describe motion. For example, we have a particle moving from place to place. We can try to identify its location, its velocity, its acceleration, and so forth. So we know how this thing moves. So in kinematics, we're focused on addressing the question of how things move. How things move. But what we left untouched was the subject of why an object moved the way it does. The reason behind motion, that is. And that is the subject of what's called dynamics. So we're now getting into a deeper understanding of mechanics by studying what causes motion. What's the reason behind motion? In other words, the question is now why? Why does an object move the way it does? In doing so, we'll be introducing new concepts. Of course, one of the obvious new concepts would be the concept of force. We all know that if you exert a force on something, it's going to cause the motion to change. You push a cart, you push it hard enough, the cart is going to move. You pull it hard enough, it's going to move, and so forth. So obviously, when it comes to dynamics, we have to study force. Now, there are different ways to classify forces. Physicists like to classify forces according to their physical origin, the physical nature. To this end, we've identified 4 types of distinct forces. Gravitational, that has to do with weight. Electromagnetic, weak nuclear force, and strong nuclear force. These are fundamentally different forces. They have different physical origins. Even though the general trend, as far as physicists are concerned, is we're trying to find a generalized description, a general theory, which would involve all these forces under the same theoretical umbrella. That, of course, would be a great thing, would be a great achievement, because in a single theory, you can explain all these forces, how they interact, how they make things work. That will be the theory of everything. Okay, the so-called theory of everything. Of course, that will be a dream come true for physicists, and we're working on it, as a matter of fact. Now, so far, the theory of everything is still elusive. The best we could do is the so-called GUT, Grand Unified Theory, which pretty much unified all the other forces except for the gravitational force. The gravitational force is just so difficult to incorporate into other forces. But when you exclude gravitational, you get all these other forces in, we get what's called Grand Unified Theory, GUT. So we are getting close to the so-called theory of everything, even though this is still a very hard subject being worked on. Okay, now as far as we're concerned, for Physics 1A, we don't have to get into the details of the physical nature of these forces. Rather, we have more practical ways to classify forces. Okay, we're going to classify forces according to whether you have to make a physical contact for that force to act. In other words, we're going to look at contact and non-contact force. That's a different way of classifying forces, and it's far more practical as far as we're concerned. What's a contact force? Well, an example of a contact force, for example, if I push the table, my finger is touching the table. There is contact between the finger and the table, and then of course, there's a force between these two, the finger and the table. That is an example of a contact force, okay? Or if I pull something, I have to grab the object and have to pull it. I have to make contact, right? These are examples of contact forces. Now, what about a non-contact force? Well, that is a force that can act remotely without 2 objects touching each other. What's an obvious example of a non-contact force? Well, gravitational force, of course, right? For example, the Earth and the Sun, there is obviously a gravitational attraction between them. That is why the Earth moves around the Sun in a near circular orbit. It's because the Sun is pulling on the Earth. Okay, that is an example of a non-contact force. And there are other non-contact forces, but we're going to focus mostly on gravitational force as the non-contact force that we study in Physics 1A. Now, the laws of motion, that's what we study in this chapter, basically the essence of dynamics. And it's mostly attributed to this one physicist, the one and only Sir Isaac Newton. Many believe that Sir Isaac Newton was not only one of the greatest scientists of all time, he perhaps was the greatest. And many physicists believe, most physicists believe, he was the greatest physicist who ever lived. So, what was his achievement that made him deserve this kind of lofty assessment? Well, Sir Isaac Newton was born in the year 1642, on the Christmas Eve of that year, actually. Incidentally, that was also the year the great Galileo Galilei died. So some were jokingly saying that Newton might be a reincarnation of Galileo. Well, that may not be true. It is true that Newton did say that he was able to achieve so much because, as he says, he stood on the shoulders of giants. Of course, one of the greatest giants in his life was Galileo. Newton was born premature, but fortunately, to the benefit of not only himself and his family, but also the rest of the humankind, he did survive and lived to a great age and became the great Newton. So, among his major achievements, the Newton's law of motion, which is a set of 3 laws that we'll be studying today in this lecture, Newton's laws of motion. That's how we understand how things move. And also, Newton's law of universal gravitation. That single law explains why the moon moves around the earth but does not fall down, and yet an apple would fall down to the earth when it leaves the apple tree. It is the law that governs the motion of planets and stars in the universe. Okay, so some even say Newton's contribution to science was so great that before Newton, the laws of nature was hidden in darkness. The universe seemed to be in chaos. We couldn't explain what was going on. And then God said, "Let there be Newton," and everything was settled. So that's just a saying that it reflects people's great admiration of what Sir Isaac Newton was able to accomplish. But his contribution went far beyond mechanics. In fact, he also was monumental to the understanding of the nature of light, to optics. He, for example, used a prism to separate different colors of light from the sun. And along with his great contribution to physics, he was also a great mathematician. As you probably have heard, he invented the mathematics of calculus, independently with Leibniz. So certainly he was one of the most important figures in the history of science, and we owe our understanding of classical mechanics mostly to the great works of Sir Isaac Newton, especially Newton's 3 laws of motion, which we'll study in this chapter. Okay, so let's look at Newton's 3 laws. That will be of central importance to the entire Physics 1A, which is why we can argue that this chapter, even though it's not the hardest chapter, it is the most important chapter of the entire course. Because from now on, with Newton's 3 laws, we will be able to comprehend motion. We can understand why things move the way they do. Okay, so let's look at the first law of Newton. Newton's first law has to do with the concept of mass and inertia. Consider an object. It is in motion. Okay? Now, if it keeps on moving, the question is, does it take a force to keep it in motion? Well, our common sense tells us that might actually be true. In other words, you need a force to maintain motion. An example, of course, is a horse pulling on a wagon, right? The horse has to keep on pulling it, even though the wagon simply keeps on moving, with the same velocity. What happens when the horse stops pulling? Well, the wagon's going to slow down and going to stop, right? So this seems to be an example supporting the argument that it takes a force, in which case the pulling force of the horse, to maintain motion. Right? That seems to make perfect sense. Well, guess what? This common sense is misleading. It does not speak the truth. And it takes a genius to go beyond this superficial common sense and get to the truth. And that great genius was once again Galileo Galilei. His observation led to the so-called Newton's first law. So remember, Galileo did perform this so-called ideal or thought experiment, which we used to argue that everything of different weight should fall at the same rate, otherwise you fall into this logical trap, right? In a thought experiment, you're not doing this in the real world, rather you're just doing it in your head, right? So we're going to do another one of those brilliant thought experiment by Galileo. This experiment has to do with an object sliding down without any friction. Suppose you have a track like this, okay? You have a track like this. And this track is very smooth. It has no friction. You know, and then I take an object and roll it down. Okay, the object starts from here. Just roll it down or slide down. Any way you want to do it, as long as it doesn't have any friction. You know, with friction, chances are it's going to stop here, or slow down and stop here, and will not go up very high on the other side of the ramp. But you can imagine what happens without friction, right? Without friction, it's going to go all the way to the same height, right? Before it stops and turns back. That's obvious. Now, Galileo says, after that, let me change the track a little bit. This time, I'm going to make the track flatter, okay? The other side of the track. You know, still there's no friction, so the ball will keep on moving until, again, it reaches the same height, right? Same height as where it started. So this time, it's going to go further. It's going to go further. Now, you can keep on doing this. You can make the track even flatter, so the ball is going to go even further before it stopped and turned around. So, guess what happens next? What would you do next to change this track? Yes, how about if we totally make it flat, right? There's no inclination on the other side anymore. You see, if we did that, will the ball ever reach the same height? Well, not anymore, right? Because it never rises. But you know, the ball is never going to stop until it reaches the same height. That's when it turns around and comes back. Since it will never rise to the same height, so what happens? It will just keep on going and going and going. It will never return. Okay, this is a smooth horizontal track. All right, nobody is pushing or pulling the ball, yet it keeps on going and going and going forever. Obviously, this thought experiment is contradictory to the idea that you need a force to maintain motion. In other words, you have to keep on pushing or pulling something, otherwise it's going to stop moving. It looks like that is actually not true. Okay, this ball keeps on moving by itself. It maintains its own motion without experiencing any pushing or pulling force. And of course, in reality, there is friction to the ball. If you don't push it or pull it on a horizontal track, it is eventually going to stop. But that is when you have actually a force, which is the force of friction in this case, or air friction, or friction from the track that's slowing it down. If you totally leave it alone, if you have absolutely no force on it, then actually the ball or any object will simply keep on moving. In other words, you do not require a force. A force is not required to maintain motion, maintain the status of motion. And when I say the status of motion, I mean the velocity. Okay, in other words, if you truly leave something alone, you do not give it any force. Okay, so if F is equal to 0, then the object can just keep on moving. It will not speed up, it will not slow down, it will not turn. The velocity is a constant. In other words, the object has its own ability to maintain its status of motion, by which I mean maintain its own velocity. This ability is inherent. You don't require any external push or pull. It keeps on moving by itself. Okay, so motion does not require a force to maintain itself. The object has its own ability to maintain its motion, in other words, keep its own velocity. This is not limited to one object. It is actually a universal property of any object in the universe. In other words, any object in the universe, without the presence of a force pushing or pulling it, will keep on moving at the same velocity, will keep on maintaining its own state of motion. And that property is called inertia. So what is inertia? Inertia is the ability of an object to maintain its own status of motion, by which I mean it keeps its own velocity. Every object in the universe has inertia. In other words, if you really leave it alone, it will keep on moving with the same velocity. Okay, that in essence is Newton's first law. So what does Newton's first law say? It says everything has inertia. That's what it says. In other words, to be more specific, if you do not exert a force on it, okay, if the net force on the object is 0, then it will keep on moving at the same velocity. In other words, if it's already at rest, it will keep on being at rest. If it's already moving at whatever velocity, it will keep on moving at that velocity forever. That is called inertia. So everything has inertia. That's Newton's first law in a nutshell. Okay, now what about mass? You know everything has inertia, right? It doesn't mean everything has the same amount of inertia. Inertia has to do with the tendency to keep its own status of motion, which is to keep its own velocity. But does every object have the same ability to keep its velocity? You know, if you push something, its velocity is going to change. But how much does it change? Well, that depends on how massive the object is, right? I mean, if the object is not very massive, okay, you have a small object like this pen, you know, I exert a small amount of force, I can let it go back and forth. The velocity is obviously not a constant anymore, right? Going back and forth. So it is rather easy to do that. It does not take a lot of effort, a lot of force to change its status of motion. In other words, it has inertia, but not much. On the other hand, it takes far more effort to push a big car, okay? Now, it's probably not doable if the car is too heavy, a single person cannot actually, initiate motion. In other words, a big car, being more massive than the pen, has far greater ability to maintain its motion. In other words, it has not only inertia, but a lot more inertia than small pen. And therefore, we must introduce a quantity called mass. Mass is the quantity of inertia. Everything has inertia, but how much inertia it has is called mass. Okay, so mass is actually a value that can be quantified. It tells you how much inertia there is. Okay, if an object has twice as the mass as another one, then it has twice as much inertia. In other words, it's going to take twice as much effort or twice as much force to cause the same change in its status of motion. That is the idea of mass. So everything has inertia, which means everything has a mass. Okay, but how much mass it has, that varies from object to object. So that is Newton's first law.